Chemical Equilibrium, Part 1. Introduction to Equilibrium and the equilibrium constant expression, capital K, EQ. Equilibrium is a state of balance. We're going to abbreviate that EQ. An equilibrium can either be static or dynamic. A static equilibrium is where an object is at rest. For example, if I take this pencil and I balance it on my finger, that would be a static equilibrium. Another example of a static equilibrium is where two opposing sides are pulling on a rope in a tug of war with equal and opposite force, such that the rope is not moving. That would be a static equilibrium as well. On the other hand, a dynamic equilibrium is where two opposing processes are in balance. Let's take a look at two examples: the Earth's water cycle and a saturated sodium chloride solution. On the left, there's a real rough diagram of the Earth's water cycle where we see surface water evaporating and going into the atmosphere, and water from the atmosphere condensing and going back down to the surface. Now, we're not saying that the amount of water in the atmosphere equals the amount of water on the surface. What we are saying is that at a particular temperature, the water in the atmosphere would stay constant, the amount of water, and the amount of water on the surface would stay constant. And what's in balance would be the rate of evaporation and the rate of condensation. Now, if you change the temperature, let's say that we go to a much, much colder temperature, we would see that very much more water would form at the surface, and a new equilibrium mixture or equilibrium state between the surface water and the atmospheric water would be established. When that new equilibrium state was established, the rate of evaporation would once again equal the rate of condensation. Now, you can imagine that's what happened when the Earth was much colder and we had an ice age. If the Earth were to heat up, the equilibrium would shift towards the atmosphere, and we would see that there would be more water in the atmosphere than there was previously, and less water at the surface than there was previously. Once the water in the atmosphere stabilized to a constant amount, and the surface water stabilized to a constant amount, then a new equilibrium would be established where the rate of evaporation would equal the rate of condensation. You could imagine that with more water in the atmosphere, we could expect more storms. All right, so another example of an equilibrium, and these are dynamic equilibria processes. In other words, equilibrium situations where there's a constant flow of material back and forth. So another example is where we have solid sodium chloride and a saturated solution of sodium chloride above it. So some of the solid sodium chloride, some of the crystals, would dissolve and go into solution, and some of the particles that were dissolved would come out of solution and become crystals again. And there would be a constant flow of particles from crystal to solution and from solution to crystal. And when those two processes were in balance, an equilibrium would be established. And like all equilibria, it would also be temperature dependent. The balance point would be temperature dependent. Those are two examples of dynamic equilibriums or equilibria that are physical processes. An equilibrium can involve a chemical process as well. A chemical equilibrium occurs when there's a chemical reaction that's reversible, and the rate of the forward reaction equals the rate of the reverse reaction. The reaction continues to progress back and forth, so it's a dynamic equilibrium. So the equilibrium state or equilibrium mixture is the balance point where the concentration of the reactant stays constant and the concentration of the products stays constant. An equilibrium equation would be written like this: reactants with a half arrow pointing towards the products and another half arrow pointing from the products to the reactants. Going from the reactants to the products would be considered the forward reaction, and going from the products back to the reactants would be considered the reverse reaction. Again, we use two half arrows when we write chemical equations that are reversible for an equilibrium. Here's an example. We have N2O4 gas that's colorless reacting to produce two NO2 gases that are brown, and that reaction progresses in both directions, forward and reverse. So if we write the forward reaction, it would look like this. N2O4 produces two NO2s. And if we write the reverse reaction, it would look like this. Two NO2s produces N2O4. So rather than having to write two chemical equations, we just put half arrows pointing in both directions. We can say the rate of the forward reaction, represented with F, is equal to the rate constant of the forward reaction multiplied by the concentration of the reactants. Now, if this were an elementary reaction, you might remember from kinetics that we can express the rate law based on the molecularity. So since there's a single molecule reacting, this would be concentration raised to the first power. It would be first order with respect to N2O4. And we can say that the rate law for the reverse reaction would look like this. Notice that because we have two molecules of NO2, assuming this is an elementary reaction, this would be the concentration of NO2 squared. It would be second order with respect to NO2. Now, if you would like to know more about kinetics, you can take a look at some of the videos that are posted on kinetics. So we can say that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So at that point, the concentration of the N2O4 would stay constant, and the concentration of the NO2 would stay constant. So if we rearrange these two rate expressions that are equal to each other, such that the concentration of NO2 squared divided by the concentration of N2O4 is equal to the rate constant for the forward reaction divided by the rate constant for the reverse reaction, what we have is two constant values. And that gives us a single constant that we could, combine from those two, and that's called the equilibrium constant. Now remember, that's temperature dependent, so we always specify the temperature at which that equilibrium is established when we see an equilibrium constant. So to better understand that, let's take a look at a few graphs. We can say that at equilibrium, the concentration of the reactants and the concentration of the products no longer change, they stay constant. But the forward and reverse reactions do continue to occur because the equilibrium is dynamic. So at equilibrium, let's take a look at this reaction where N2O4 is in equilibrium with two NO2s. If we graph out concentration versus time, where we start with zero amount of product and a certain concentration of reactant, we would see that the concentration of reactant would diminish as the reaction progresses, and the concentration of product would increase as the reaction progresses, and there would be a point where equilibrium is achieved, where the concentration of the product NO2 is constant and the concentration of the reactant N2O4 is constant. Now, if we were to change the temperature, where these lines level off might be different. They might be a little bit higher up or lower down, depending on where the equilibrium point would be established, or the equilibrium state would be established. Now, it doesn't matter how much of the reactant concentration or product concentration we start with. In any proportions, we're always going to, at a given temperature, reach a certain point where the concentration of the product and reactant will become constant. That's where we get to the equilibrium state. Now, the rate versus time graph on the right-hand side here shows that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So the N2O4 making two NO2s happens as fast as the two NO2s making N2O4s. We can substitute in from the rate laws, those two expressions, and say that here we have the rate of the forward reaction, and here we have the rate of the reverse reaction, and at the equilibrium state where equilibrium is achieved, those two rates become equal. Now, the point where those two rates become equal is also temperature dependent. So an equilibrium mixture or equilibrium state is attained at any given temperature for any initial amount of reactant or product. So it really depends on what reaction is occurring, what chemicals are involved in the reaction, and it depends on the temperature as to where the concentrations flatten out on this graph and where the rates become equal on that graph. In other words, where the equilibrium state is achieved. Now, from experimentation, we establish laws in science. They tell us how things behave. So we have the law of mass action. Now, this works for all equilibrium reactions, even the ones that are not involving elementary reactions like the example that we just looked at. We can say that if we have A moles of chemical A reacting with B moles of chemical B in a reversible reaction with D moles of chemical D and E moles of chemical E, that the equilibrium constant, capital K, EQ, can be expressed in terms of the concentration of the chemicals. And from experiment, we know that this is what the equilibrium constant would be equal to. This is the equilibrium constant calculated with concentration. That's why there's a subscript C. So the concentration of chemical D raised to the D amount of moles multiplied by the concentration of chemical E to the power of E amount of moles divided by concentration of chemical A raised to the power of A amount of moles multiplied by the concentration of chemical B raised to the B amount of moles of chemical B. So it's the product of the concentration of the products. These are multiplied here, they're not added, divided by the product of the concentration of the reactants raised to their respective amounts of moles as powers. Now we can do this for pressure as well if we have a gaseous reaction. So here we see the equilibrium constant calculated with pressures for gaseous reactions, where now instead of saying C for concentration, we have P for pressure. So this is Kp. So the partial pressure of chemical D to the D power multiplied by the partial pressure of chemical E to the E power divided by the partial pressure of chemical A to the A power and the partial pressure of chemical B to the B power would give us that as the equilibrium constant expressed with pressures. The value of the equilibrium constant, KEQ is the generic way to write it, at any given temperature does not depend on the initial amount of reactants or products, nor whether any non-reactive substances are present. It just depends on what the reaction is and what the temperature is. So we can say that KEQ is temperature dependent always. KEQ has no units, and we're going to take a look at that in the next few pages. And KEQ does not include pure solids, pure liquids, or any solvents in the reaction. So in order to understand why there are no units for KEQ and why we can ignore solids and liquids, we need to understand that KEQ is really derived from kinetics and thermodynamics of reactions. And it's based on activities. Now, the activity of a chemical is just about equal to the concentration of a chemical for dilute solutions. Activity is the amount of substance divided by a reference state. So if we look at this table here, we can see the phase of the substance, aqueous, gas, liquid, and solid. The reference state, for an aqueous solution, the reference is a 1 molar concentration. For a gaseous reaction, we have the reference is 1 atmosphere partial pressure. For a liquid, the reference is just having pure liquid, and for a solid, it's pure solid. So we could say that the activity of a chemical that's aqueous would be the concentration of that chemical in molar or molarity divided by 1 molar. For gases, it's the partial pressure in atmospheres divided by 1 atmosphere. And because the reference state is pure liquid and pure solid, the activity is 1 by definition for liquids and solids. Now, activity is something that's really not important until you get to upper levels of chemistry. But we can see that because of the way that activity is structured, molarity divided by molarity, atmospheres divided by atmospheres, or just 1 and 1, activity is set up to be a unitless value. And activity, A, is 1 for any pure solid and liquid. So we can say that if we have this chemical reaction, the equilibrium constant really should be based on activities where A is the activity for those chemicals. Now again, activity is something that's really addressed in upper level chemistry courses, so we can stick with Kc and Kp expressions. Now there's another way we can look at this too, because without having to get into a big discussion about activities, it seems a little bit confusing, and we can just say that pure solids and pure liquids have a constant concentration. If you increase the mass, let's say that we double the mass of a pure solid or a pure liquid, well, that would just double the volume of a pure solid or pure liquid because they're condensed states of matter. So the particles are all tightly packed together. If you double the amount of particles, they would take up double the space. And the equilibrium expression, or the equilibrium constant, only needs to deal with changing concentration. Since changing the amount of solid or liquid in terms of the mass or the volume wouldn't have any effect on the mass to volume ratio or the concentration, we can ignore solids and liquids in the KEQ expression. We're going to look at KEQ in more detail in coming videos.